Hey, Ignite students, we're still here. It's still a snow day. So everybody else is learning online just like you. We're back. Okay. Fossil record? That's today. Fossil records today. Sorry, relative dating. That's where we're at. Relative dating is the stuff of last week, and it just slipped my mind for a second because I hit record. That's why. So we're going to look at some of those basics. I didn't have any images last time, so let's look at some of that. Law of superposition, right? Law of superposition, the oldest stuff's on bottom, and then you lay down another sedimentary layer, and then another, and then another. You can see some of the Grand Canyon is absolutely geology 101. Like, it's how did that Colorado River cut through all these layers, and you expose all of these different things. So the Khabib limestone, all right, the Toroillo formation, Coconino sandstone, the Hermit Shale, and the Supai group. You've got all of this stuff, old stuff on bottom, younger at the top. We're going to leave that one and come back to it in a minute. This one, the law of the principle of originally horizontality. Yeah, horizontality. Well, something came in and upended that. There was an inclusion, there was an uprising, there was something to bend and pressure that up. So all of these rock layers were originally flat, and then something has disturbed it later. All right, so law of superposition, principle of originally horizontality, cross-cutting. So I talked about the layers, and then there was a fault, and then it changed, and then new layers on top. So you could tell fault A, and over here, the dike A, which is a tube for magma that goes straight to the surface. Which one's older? Fault A, because it only goes up through this, not the dark sandstone, but this light sandstone layer. That's where it stops. So it happened, then the fault split, and then these new layers were put down on top. And then this dike came piercing through. So you can order this stuff based on how many layers it cuts through. So that's cross-cutting relationships. All right. Inclusions. Okay, this was the tough one. So remember, the inclusion is the igneous rock that just kind of wells up and puts the mound, like the magma. It doesn't really hit the surface, but it just bumps up what's above it and stuff. So you get this inclusion of igneous rock right here. All of this on top is eroded, but even some of the igneous is eroded. This was the hard part to explain without seeing it. Later, you put more stuff on top of it. Well, because this is broken up, you get little bits of this inclusion in this bottom layer of the next sedimentary layer. That's the inclusion. So we know that this had to be broken up before you put down the next layer. All right. So this not a good image to show, but it is just deformed here, which is okay because it's about an unconformity. So I just mentioned unconformity broadly. There are like three types. This is an angular unconformity, okay? So you get upwelling, which means that the water is going to move away. Sea level is going to stay the same. And when you get uplifting of a landmass, sea level doesn't reach that land anymore. Then you get erosion, and then later you can get new sea level deposits. Well, that's great. This goes all the way across. This goes all the way across. This one's broken up. This one's broken up. And that is the angular unconformity, because it's up at an angle from the old upwelling, and it is broken and does not match what's directly above it. It matches what's over here. Like, you've got to zoom out sometimes and see some of this. Okay? The other types of unconformities, okay, there are disconformities and nonconformities. There's three types of unconformities, or angular unconformities, disconformity, and a nonconformity. We are not super worried about all of that right now. By the way, this is Colorado River. This is the Grand Canyon. Okay? It's very hard to see. This image is too small. I wish you were online. I wish you had some of the book, but this is good. So, Grand Canyon, Zion, Bryce Canyon. 3 national parks, 3 beautiful places I would love to go visit. I've actually not been to any of those. I need to travel more, right? Yeah. Oldest at the bottom. And if you look at the layers of the Grand Canyon, what you find is that this layer, this layer, this layer, and this layer match these couple layers over here at Zion. And relative dating says this layer is newer, this layer is medium, this layer is older. The oldest layer here matches a layer over here, then you can start to date more layers. Then you know that this one is older than this, which is the same as this, so this one's young, medium, old. And you repeat that at Bryce Canyon with these layers, and so you get young, not so young, a little older, and super old. And so relative dating across big place and big space, you can put a lot of things in order. All right. Which is part of what we want to start with today. The correlation. So we didn't mention this last time. Correlation of rock layers is when you take exactly this and you look at rock layers here and then you look at different ones across the globe and you try to put all of this together and get a timeline for the Earth. And you zoom way out and put all this together. Okay. Yeah, so rocks of similar age have to be matched up. That's what we're talking about. All right, so I left that. We can get rid of that one. Ordering the Grand Canyon, just because we were coming back to it. Okay. Here we go. Fossils. We're going to use this website for a minute. We're going to talk just a second. Fossil is what? The impression, the remains. It's remains or traces of prehistoric life. Be careful. Do not immediately think dinosaur bone. Doesn't have to be a bone. Doesn't have to be an animal. Because ferns leave impressions. And believe me, some plant fossils are just as important as animal fossils. So any living life and its traces. So any kind of thing that it leaves behind. You got to have sedimentary rock or sedimentary or just sediment or sedimentary rock. That's where they're formed. It's super important, and it tells a history. It tells a story of the things that have lived on this planet. All right. So what do we have? You have altered and unaltered fossils. Okay. You have, those are the 2 broad categories, but beyond that, you've got molds and casts, carbonization, petrification. So we're going to glance at some of these different types. Here we go. There we go. Molds and casts. What is it? It's exactly what you think it is. The fossil is put into the sediment. Later, erosion or whatever, or erosion, mineral water, removes the fossil, but the impression it made in the sediment has now turned to sedimentary rock, and so the impression in the rock remains. Again, we could read through this, but we're fine. Okay? So that's a mold or a cast. Scroll back down. Imprints and impressions. Impressions very similar to a mold or a cast, right? So you could do this. This is a fish, obviously, but they're very, very shallow molds. That's the biggest difference. All right. Let's go back. The other type we want to look at, permineralization. Okay, we're going to pause on that for a second. Carbonization is what we're going to look at here. Insects? No, those are not insects. Those are not even imprints. That is like an outline. That's a residue. When you squish them down, the liquid in their bodies, the soft tissue, the air comes out. We've got carbon in our bodies, and you can get carbon to leave this oil and this casting, carbon in your pencil, carbon and graphite in your pencil. Essentially, you can get an impression, not an impression, don't say impression. You can get carbon, it's a chemical change to leave a trace and an outline on the rock that remains. Not easy to dig that up because it's literally just that thin, right? Why isn't the bug there? Because bugs have hard exoskeletons? No. Not when you're talking about pressures of Earth. Like, that's not, the exoskeleton's not going to stand up to that. It doesn't even stand up to a shoe, right? So, what makes a fossil? Well, okay, let's keep looking at a couple different types and see if you can gather some of the other things that go with this. Amber. That's a real thing. That's not just a Jurassic Park like fictionalization. Now, drilling in there and extracting blood and DNA from the mosquito, a little far-fetched. But yes, amber and other resins, tree resins and sap, you can collect and see fossilized insects. All right. Replacement mineralization. This one's a little different than the casts and molds, because casts and molds are hollow. This is hollow, but this is the opposite. So the bone, instead of being washed away and leaving just the impression, the water has minerals in it. It's not pure H2O, all water. When it comes in, the minerals actually seep into the pores and the cavities in the element, in the shell, and they harden the shell, so the shell now is part shell, part rock, and survives better. So because it has these other elements in it, it becomes stronger and stays through all the weathering and erosion and years. Okay, let's see. Indirect evidence. There's a couple more we want to look at. Recrystallization, freezing, trace fossils. Trace fossils aren't really about fragments. They're about tracks. This is indirect evidence. So footprints. So you can actually see motion and you learn about gait and other things if you happen to get a series of footprints, which is the craziest thing. Problem is, mud's soft. And when you step in mud, there's a footprint today, but that footprint washes away fairly easily. You have to have very, very specific conditions to preserve that. So that's why they're not crazy common, but they are around. All right. There was one other I just saw, and then we're going to wrap up. Unaltered remains. This is the good stuff. Now, you look at this and say, what is that? That's a tooth. That is a molar. Big, flat tooth. You got roots going down in here. It's a mammoth molar. 13 centimeters long, 7 centimeters wide, 13 tall. Thing is big. All right, 13 centimeters is 6 inches almost. 5 3/4. I don't know. It's just less than 6 inches. That's a tooth. Bone, sure, but tooth enamel is actually, I know we say enamel soft, take care of your teeth. Enamel protects well. That's what it's designed to do, and it can preserve teeth better than bone sometimes. And that is preserved better than soft tissue, which is preserved, every different type of tissue is preserved differently. How in the world do we use all of this stuff? Okay. Oh, what are some of the things we need? Rapid burial. Have to have hard parts. Those are some of the things that help do this. I do have a question though. The fossils you think about, the fossils we have, the fossils in our museums, they are biased. They really are. And that's odd to say that this inanimate object is biased. It has a perspective. But here's the thing. Lots of fossils of animals with hard bones. How many fossils of jellyfish are there? The soft bone, no bone animals don't get any respect. They don't get any. So there could have been bazillion, blobfish living in the ocean, and what? We wouldn't know as much about them because their fossils are going to become more rare. So these fossils are important, but you've got to know that they don't represent everything that is, was, and will be, right? They only represent a portion, and they represent a skewed portion of what used to be alive. Okay. Other things, so late 1700s, William Smith, English engineer, ditch digger. He's digging canals, and he begins to notice that these fossils are not randomly thrown about. Top layer has this kind. If you dig a deeper canal, it's got this kind. If you dig something really deep, it's got this kind. The fossils are layered. And then as he's digging around England, he recognizes, well, this starts in the middle layer, and then the deep layers below it. He recognizes that this stuff is ordered. So comes up the principle of fossil succession. All right. Fossil organisms succeed one another in a definite and determinable order. Therefore, any time period can be recognized by its fossil content. It's the same as the layering in the sedimentary rock, right? The law of superposition. So that's the idea. Index fossils, last little vocab word for right now. Index fossils are a fossil that is well known, it's widespread, and we know something cool about it. So if we find a specific type of bird, good news, this bird, geographically, it was all over the place, right? Because it migrated here, there, and everywhere. So this bird covered a large portion of Earth. And you want, if it only lived for a very short time geologically, okay, then what you could do is link the rocks in here, in different parts of Earth with this one fossil type and know that all of those rocks happened at a similar geologic time. That's what an index fossil is. So an index fossil is a specific species or type of fossil that was short-lived geologically, widespread geographically, and that we can link different parts and different rocks around the world. All right. Fossils help you interpret the environment. Last little thing. What does that mean? What do I want to say about that? If you go out in the sand and you dig around and you find fish bones, that tells you at some point in the past there was a fish there. Well, maybe a fisherman brought him in. Okay. But there would still have to be water nearby. So the thing you're standing on that looks like a dry, dusty desert now maybe used to be a lake bed. That's just an example, right? It's a broad example. Don't let what you see now affect what you think it could have been, right? The Earth has changed dramatically over geologic time. So things that are high elevation, low elevation, elevation changes, climate is, weather is, like water, all of it's changing. So what looks like a dry lake bed used to have water in it. And so it used to be full of fish and other animals. So I guess that's the last little thing. Have a good day. There'll be a small assignment on Canvas to go with this. Look me up a cool fossil. I'll talk to you next time.